information dynamics, as I will try to explain to you, in minimally cognitive agents, and this is joint work with Paul Williams. So hopefully you will not be too unhappy to learn that this is a continuation of discussing the same agent that I talked about earlier. So just to very quickly remind you, this agent solves this relational categorization task where we drop one object, a Q object of various sizes. Once that object reaches the agent and is removed from the environment, the second object falls, called a probe object of various sizes, and the task is to avoid the second object if it's smaller than the first object. I'm sorry, catch the second object if it's smaller than the first object, avoid it otherwise. So it's a smaller than the relational discrimination. And sorry?
Are you referring like that?
Yeah.
What's that?
I think of slides are not so visual with the light on.
Oh, well, we can turn the light off if you want. I was just afraid it was getting too dark. Yeah, okay. Everybody will be asleep, including me, if the lights are off, I'm afraid. Okay, so earlier I kind of went through this story of how one of these agents works dynamically. Oh, first of all, last thing I need to remind you of, there were the passive solutions and the active solutions. The passive solutions just sit still while the Q object falls, and then they actively move during the probe stage. The active agents are moving during both stages. Okay? So I gave you a dynamical story of how the best passive agent works. And now what I'd like to do in this talk is sort of switch hats and now look at this same agent from the point of view of information theory rather than dynamical systems theory to see how that same agent's mechanisms would be described, operation would be described. And then I'm also going to talk about one of the active agents, which I didn't talk about earlier, because it's easier to do it quickly and simply in terms of the information theoretic analysis. Okay? So just very quickly, I'm using for the most part, very simple tools for information theory. So the key concept in Shannon information theory is the entropy of a random variable. It's basically a measure of uncertainty. If I make a measurement on this random variable, if I always get the same result, because it's just constant, it just returns the same thing, there's no uncertainty about what a new measurement is going to see. Okay? So that has an entropy essentially of 0. The other extreme is a maximum entropy situation where the random variable is sampling a uniform distribution. So I have no information about what value I'm going to see next time, because it's completely independent and completely equally balanced across all of the possibilities. That's a maximum entropy situation in Shannon's terms. We're not actually going to be using entropy directly. As most people, we're going to be using mutual information, which is a relationship between two random variables, and it basically measures the extent to which my uncertainty about one random variable is reduced by knowing the value of another random variable. Okay? So traditionally, Shannon information is applied by sort of averaging over everything else. So you end up getting a number between two random variables that measures the mutual information between them. That's not going to be sufficient for us to apply these concepts to our brain-body environment systems. And in fact, it's not enough in many other situations too. There's this whole area of extending information theory in various ways. One of them is we want to be able to unroll these measurements over time. So we don't just talk about the mutual information between two variables, we talk about the mutual information between two variables now, and then the mutual information in the future, and even further in the future, and so on. So we start thinking about mutual information as being a time-varying quantity, and that's a straightforward thing to do. Something that's a little bit less straightforward, less common at least, is we're also going to unroll mutual information over measurement outcomes. Okay? So what this means, and this is called specific information, what this means is essentially, without getting into the mathematical details, the basic idea is how surprised would I be to find that the random variable x takes on the particular value, little x, after I've measured the value of y. Okay? So it's a finer resolution statement about the mutual information between the two variables x and y. And you can write out a formula for this, and I don't want to get into that level of detail in 30 minutes, but essentially what I've done is I've taken a single number and I've unrolled it over time so I can track that as a dynamic variable, and then I've unrolled it over stimulus, over measurement outcomes, so I can actually talk about the information about a particular stimulus outcome at a particular time, carried by one random variable about another. And then finally, there are these measures of things like the information gained or the information transferred between random variables, which you can define. This is a fairly controversial area of information theory right now, because it basically amounts to requiring one to decide on what's the right generalization for mutual information to more than two variables. And that's controversial. So we have one particular way of doing that, which we call partial information decomposition. And it's that method that I'm using to define, but I'm not going to go through the details, a measure of information gain and information transfer. And I'll just show you how those work in the example rather than going through the details. Okay. Yeah. All right, so what I want to talk about first is applying these concepts to the best passive agent. Okay, so remember, it's divided into a Q stage and a probe stage. I'm going to talk about them individually. So just to show you the kind of plots we're going to be talking about, so what this is a plot of, for all of the sensors. There are 7 sensors in that little agent. One of them points straight up, and then there are 3 pairs of increasingly obliquely oriented sensors. And what this is plotting is, over time, the mutual information in all 7 sensors between the sensor state, the sensor value, and the size of the Q object. So, for example, we see that there's no information in sensor 4 about the size of the Q object. And that's because that's the sensor that points straight up. They're numbered 1, 2, 3, 4, 5, 6, 7. And the one that points straight up carries no information about the size of the object because it doesn't give you any information about the visual angle that that object subtends. Okay? The other sensors carry information about the object size in pairs, because the objects drop straight down at the agent. And so at some point, that object intersects both of these pairs of rays, and then subsequently these pairs, and finally the outermost pairs. And you see that they carry information about the Q size, which ultimately decays to 0. And the reason why it's 0 is that the sensors in this model have no state. Okay, so they only can carry information about the object size when the object is actually present. And when the object disappears at the end, they've got to be 0. That's an important point for what I'm going to show you next. Okay, so these are the kind of plots we're going to get. I'm not unrolling these plots over outcomes yet. I'm going to do that in a minute. This is just unrolling over time. And so we can do the same kinds of things for the inner neurons. This shows the mutual information between the size of the Q object and the output and the neuron output over time for the 3 inner neurons. You see that they all 3 carry some information about the Q size at different times. I'll say more about that in a minute. And we can do the same thing for the other state variables in the system. So there's a right and left motor neuron, and then there's the actual agent position, which is the body variable in this simple model. These carry no information about the size of the object, and this is consistent with the fact that this is a passive agent. If the agent's just sitting stationary, okay, as objects fall, then by measuring where the agent is, I gain no information about the size of the object, because it always does the same thing. It always just sits still. Okay? So, because of the nature of this task, the sequential thing, where first you perceive the Q, it's removed, then you're exposed to the probe, there has to be some way to carry over information about the Q into the probe stage. Okay? So we can look at these plots and we can ask, where in the system is there any information about the size of the Q object at the end of the Q stage? Well, it's not in the sensory neurons, as I just explained. It's not in the motor neurons or X. And it's not in neuron 1 or neuron 2 because they both fall to 0 before the end. So in this particular agent, and you get different results for different agents, you basically see that there's only information in neuron 3 about the size of the Q object. Okay? So I'm just kind of showing you how to read these plots. So I want to focus in on neuron 3 and explore it a little bit more. Yeah, I guess you can see that. So this is just repeating the curve over time of the mutual information in neuron 3 with respect to the Q size. And this shows the same curve unrolled over stimulus values. And the main point I want to make here is just to show you how much information in the scientific sense, how much we've lost by averaging over this. So when we get a curve like this, we're losing the fact, for example, that there's a lot more information about small object sizes than there is about large object sizes at this point. Okay? The information about different kinds of sizes is not distributed uniformly throughout time. And you can see that, for example, the information about large object sizes reaches its maximum before the information about small object sizes. So there's some interesting dynamics about the specific information that we have about the various possibilities that we may be encountering, which these unrolled plots bring out. So just quickly then, we can calculate the information gain, which is in this case kind of a derivative, if you will. It basically tells us, it highlights when the mutual information is changing most quickly. So for example, this first feature here corresponds to a gain here, which then tails off. That's why it's like a derivative, right? You're not changing, you change, and then you stop changing again. The gain is 0, it increases, and then decreases back to 0. And so you can see that information is gained in neuron 3 about the Q size in waves. Does everybody see what I'm talking about there? Right? You see a wave here, a wave here, a wave here, here, and here. These waves of information gain are coming into the system. So where are those coming from? Well, to make a long story short, we can calculate the information transfer. And what I'm showing you is the specific information transfer from each pair of sensory neurons. And the information transferred from this pair corresponds almost exactly to the information gained in these two waves. The information transferred from these sensory pairs correspond to this, and here, and here. So what this suggests is that if we look at this information theoretically, basically all the information that is being accumulated in neuron 3, in that inner neuron, is just coming directly from the sensors. That's not necessarily the only possibility. You could have information coming from the sensors to all the inner neurons and then interacting so that some information is transferred from one inner neuron to another inner neuron. Okay? And we see examples of that, but that's not what's happening here. So I'm being a little fast in this, but I mean, I'm arguing qualitatively that you can see that this accounts for most of the information gained by neuron 3. All right, now let's think about the probe stage. So there's a lot more I could say about the Q stage, but let's jump to the probe stage. I can make the same kinds of diagrams for the probe stage as I did for the Q stage. We could ask, where is information about the Q size? Where is information about the probe size over time spread across the components of these systems? Okay, you can do that, we've done it, but again, in the interest of keeping the story short, what really matters for the discrimination is not the absolute size of the Q object or the probe object. The discrimination is supposed to be based on their relative size. So we want an information variable that's related to relative object size, and what we can do is I can just define and derive a binary variable that takes on the value 1 whenever the probe is smaller than the Q, and takes on the value 0 whenever the probe size is larger than the Q. I just define that. It's computable from the actual properties of the system. Okay? And then we can look at the information flow of this relative size variable rather than the absolute sizes. And to tell the story, I think, in the cleanest way, I want to start at the output. So we can look at the agent's position over time and ask how much information is in the agent's position about the relative size of the two objects. Well, in the passive agent, until you start to move, as I said before, there's no information about anything to do with size if you're just sitting stationary. It's only when you start to move, if there are differences in the way you move according to one sort of relationship versus another, then you're going to see an increase in size, in information about relative object size, and eventually it tails off. The thing that's important here is that this is when the discrimination is actually reflected in the behavior. So we can now trace back and say, where did that relative information increase come from? And the most obvious place to look is the motor neurons, given the way this system works. What moves the agent is by the motor neurons activating. Okay? So we can compute the relative the information about relative object size in the right motor neuron and the left motor neuron. And first, qualitatively, I will point out that the information increases in the right motor neuron, then the agent position increases, and then information about in the left motor neuron appears. So information theory is correlational, not causal, but this suggests a causal story, which one would then need to check, that it's the increase in information in the right motor neuron that results in the increase in information in the agent's position, and then it's that movement unfolding which turns out to start to be reflected in the other motor neuron. Okay? And then finally we can go back another step and ask, where did that information come from to drive the right motor neuron to have the information it needed? And we can go back and look at the relative object size information in each of the inner neurons. Okay? And again, qualitatively, I'm about to show you a little more carefully, but we see that there's a fairly sharp increase in the availability of relative size information in neuron 1, that then somewhat slightly later you see the increase in the right motor neuron, and then finally you see the increase in X. So again, this only suggests from this level of analysis that its information is carried from the inner neuron 1 to the right motor neuron and ultimately to the position. Now I want to reiterate to you that these are plots of information, not neuron activations. They look like neuron activations, but they're not. So for example, just to drive that point home, this increase in information about relative object size in the right motor neuron actually corresponds to a decreasing activation in the right motor neuron. Because the way this particular agent works is that it turns on both its motors and then differentially turns off its right one in order to make movement. That's just a particular way it evolved. Different ones will evolve differently. So you can't read these as neuron activations, although they're not unrelated to neuron activation. And then you can actually compute explicitly the information transfer, and what you'll find is that indeed information is transferred from the right motor neuron to the agent position, and from the inner neuron 1 to the right motor neuron, corresponding to these qualitative points I made earlier about what the curves look like. Okay. All right, I don't know, who's keeping time? How much do I have? Because I want to talk about the active agents now. 10 minutes? I think that's fine. So we can do the same thing with the active agents, which I haven't talked about before. I didn't show you a dynamical analysis of this. And when we do it, we're faced with two mysteries. The first one is illustrated right here. If we look at the specific information about Q size in an active agent, what we find is at the end of the Q stage, it's 0 in inner neuron 1, it's 0 in inner neuron 2, and it's 0 in inner neuron 3. Okay? So the active agent contains no information about the Q size in its inner neurons, and yet it makes the relational discrimination as well as the passive agent does. So that's the first mystery that we're going to need to solve. But there's another mystery. So the first one is, where is the Q size information stored for later comparison? But there's another mystery too. If during the probe stage we ask where is the probe size information, we find another mystery, which is that in every single sensory neuron there's absolutely no information about the size of the probe. So informationally, this agent can't remember the size of the cue, and it can't perceive the size of the probe, is what these two results suggest. Is that clear why that's puzzling? Right? Because it's still as good at solving the task as the passive agents. Okay? So how does it extract the probe size and compare it to the cue size if it can't perceive the size of the probe? Okay? Yes? So, you can pause a minute so you're well and truly bothered by this, because it bothered us. So, we want to actually figure out, well, what's going on here informationally, right? So, it turns out what the active agents, although they have no information about the cue size in their inner neurons, that's not the only state variables in this system. And in particular, if we look at the positional variable, okay, there's a nice build-up to a very high value of information about cue size in the body position. Okay? And let me show you behaviorally what's going on there. What's going on behaviorally is that during the cue stage, the cue object falls and the agent moves away from the cue object a distance that's proportional to the size of the cue. So it's offloaded the memory, the storage of size information into its position relative to where the objects fall. Okay, so it moves off a little bit. If it's a small object, it moves off further if it's a big object. What about the other issue? That there's no information. So now we know where the cue size information is. It's still in the system. It's just not in the brain, basically. But what about this other problem? That the agent doesn't seem to even be capable of perceiving the size of the probe, and yet it's able to reliably make a size discrimination. Well, it turns out here that this is asking about the information in a sensor. But we can also look at information conjunctively. We can look at information, it's called synergy is the technical term. We can look at synergistic information that's stored in combinations of things rather than just individual components. And I won't bore you with all the details because the result is clear enough that although there's no information about probe size in the sensor, there is a lot of information about the size of the probe in the synergy between the sensors and the position. Okay? So if we consider just the position because it can adopt, if we consider just the sensors because it can adopt different positions, there's no reliable information available in that raw signal. But we can consider it in conjunction, synergistically, with the position that it adopts, then there's a lot of information. So what's going on here then, in a nutshell, is that, well, so this is called information self-structuring, essentially, where what you're doing affects the information content of what you're actually perceiving. This is a simple example of that. So what's happening is, again, during the cue stage, the agent moves to some offset relative to the cue object based on how big that object is. And then during the probe stage, what it does is it starts moving back towards the midline. And for a small object, for a small probe, it takes longer before it encounters the probe object. And for a large object, it doesn't take as long before it encounters it. So not only has this agent sort of offloaded the memory, the storage of the cue size into the environment, it's largely offloaded its decision into just a perception. It just has to perceive, when I see the object, I instantly know whether it's smaller than or larger than because of the way I've structured the whole interaction with my body. Okay? So this makes a nice bookend to the passive case where the story is almost entirely neuronal and internal. Here's a case where the story is almost entirely external, embodied and situated, and the nervous system is doing, very simple things like making me move in one direction versus making me move in another direction. And the whole memory, storage, and relational categorization decision is all made in the body and the environment in their interaction. Well, I think I'm going to tail off here rather than... So, the thing that we're really interested in with this model is we have this dynamical story, which I've told you part of. We have this information theoretic story that I've told you part of. There's more details to each of them, but I hope I've given you at least a sense between these two talks of what we can do with these models. What we're, of course, really interested in is something that, as far as I know, nobody has been able to do, or maybe even been stupid enough to think to do, in any system, which is we can ask about how these two stories relate. Okay? We can look at the structures that we see in the dynamical system story, like this curve of states, or this two-dimensional manifold of states as they depend on the Q sizes or the Q and probe sizes, and those things evolving over time and encountering bifurcations that tear them apart and so on. We've got that dynamical story. We also now have this information theoretic story about how different components or synergies of components, information theoretically, carry information about various aspects. And so, you know, the obvious thing to do to me is to oppose those two stories, you know, lay them over top of one another and say, how do they correspond? Because the question isn't, will they correspond? Of course they do. It's the same model. I mean, it's not like they're going to be inconsistent, but they certainly highlight different features and they use different explanatory vocabulary. And so it's very interesting to see how they fit together. We have the beginnings of a story about how that works, but it would take me more than 5 minutes to even tell you the beginnings. And very much this is ongoing work. But I guess I will say this much. I really think it's going to be possible to formally and mathematically exactly describe the connection between these evolving manifolds in state space conditioned on various parameters of the task, like these object sizes, and the corresponding information theoretic quantities that are pulled out. Whether or not that has any relationship to what people used to mean by information processing and or computation is an open question, which I hope I've been careful enough to make clear to you I'm not really that interested in, because I look at these as just two different mathematical languages that we can apply to a system. They give us different perspectives on that system, and then we can ask what the relationship between those perspectives are. And I view my job as just laying stories like this out, and like I did with the representation question earlier, sort of confronting you with the results that we see, and getting you to think more carefully and more deeply about whatever position you might take on information processing, computation, representation, and discrete versus symbolic, whatever your favorite philosophical controversy might be in cognitive science. The point of these models is to try to push you in a very concrete way to confront some of those questions. So I think I'll stop there.
Any question? So I'm just I just want to know your thoughts on the fact that information theory measurements are purely relational, and just to put a kind of example to what would happen and how would you interpret that, is that we could have an additional variable, for example, which is the color of the agent, which has a shadow independent on the object that is falling and its size. One could measure that as a variable of the agent. That'll have a lot of information. And well, I'd be curious to know, because there will be clearly no causal connection between this color or shadow and the behavior of the agent. How would that?
Yeah, as I said before, information theoretic quantities are correlational, not causal. So there are two ways to address that. One way is there are these interventional techniques, which sometimes are called information lesioning, for example, where you actually go in and manipulate the system in some informational way, like you randomize over something that was not randomized over before. You informationally perturb the system without actually cutting a connection, which actually does a lot more violence to the dynamics than just randomizing over things to see if there's really any information in that signal that's being used, right? Because if there's some information in a signal, but randomizing over it doesn't change the behavior of the system, that's evidence that it's not playing a causal role. So that's the standard way of doing it, to go to interventional techniques. But when we have a dynamical system story of the actual mechanisms, we don't even need to do that. We know what's going on in the system causally, mechanistically, right? And so we can relate those two things. And everything I've described to you informationally in the system turns out to be causally important. But I want to be clear that wasn't necessarily true, right? And in fact, you're right, there are other informational quantities we could look at, not even inventing one. We could look at, for example, information about how far away the object is. Right? I'm sure you'll see, elements carrying information about that, which doesn't really enter into the decision-making process. The other thing that's really interesting that people that maybe haven't thought about this before might find surprising is that the same element can carry information about many, many different things. And that seems a little weird until you actually look at dynamically what it means for it to carry all these different kinds of information. And it's very simple to see why that's the case. Oppositely, you can also have information about something, the way I showed you with the synergy, spread across multiple things. Okay, which is also something that's a little odd if you think about information processing in a traditional discrete symbolic sort of manner, rather than what you might want to call a generalized information processing, which is these continuous information flows across many components over time, which is more of the picture that we're looking. Did that answer your question?
Absolutely.
Okay.